as one increases, other one increases or not. It is not just correlating two variables. We have a concept of one causes the other. We go with the concept of causation and then do the analysis. So these are all some simple examples. So this is basically the direction of the relationship and the extent of relationship. It's a positive correlation, or if there is a correlation exists, then what is a change as we change one variable in the dependent variable on the other variable. So usually we call it as association, means when you correlate two categorical variables. So for an example, gender and coronary heart disease, yes or no. We use the word, is there any association between the two, rather than saying, is there any correlation between the two? Usually we talk about if there's any correlation, but typically that is correlation is specifically used for continuous variables. So these are all the range. Please remember that the correlation range is from -1 to +1. So for the R square is 0 to 1. Okay. Now the Y variable follows a normal distribution, and we are not going to see anything about non-normal now. This is very important. This is a positive correlation. And this, you know, what is negative correlation and what is no correlations and so on. So no correlation. This scatter plot is the step one diagram that you need to do to study the direction. And this is, it has twin purposes. The scatter plot, as I said, the binary univariate analysis and regression analysis. It serves two purposes. One is to see, is there any, what is that kind of direction going on in the data? The next one is there any outlier in the data? Please remember, this is very important because the outlier is very sensitive to any regression analysis. Sometimes you see a scatter plot like this, which the linear is not suitable for this kind of diagram. So therefore, you would go for curve linear regression, especially gestational age and birth weight. It is not linear. It is after some time it gets flattened. It's a sigma-shaped curve. So ideally, if we all do is just the linear regression analysis for gestational age and birth weight. Ideally speaking, you should do a quadratic term added into the linear regression model. So that is something which we will see. Let us not go into the details. So this is, if there is an outlier that causes big problem. If you wanted to have a very good regression analysis, put a couple of outliers in the model, you'll get a very high correlation and so on. I'm just joking, but this helps you to, figure out what are kind of outliers are sitting there in the data. So just please go through this one. There is this outlier here. So therefore, you just see, you wanted to report it and delete it, and report it, and or you just edit your data and deal with that. So this is what we said, and these are all the purpose of doing regression analysis. Basically, we are interested in dealing with the confounding variables in the data and also derive regression equations. That is a prediction modeling concept in regression analysis. This is to adjust for confounding effect in epidemiology. This is the main purpose we have. Now let me go into interpreting the regression coefficients. There are two drugs used in animals. This is the blood pressure values. Drug B and drug A. Say for example, if you take out the drug from the animals, what kind of blood pressure that animals will have? Any idea? Constant. So if drug becomes 0, that constant tells you that this is the baseline blood pressure that animals had. So as you add the drug, it increases as you increase your dose. Okay. Now, because the dose is different, but you see here, either drug A or drug B I use, if I remove the drug, they all come back to the normal blood pressure of 20. Is that okay? So that is a significance of dealing with constant term in regression analysis. What does it mean to us? It means a lot to epidemiology. Say, for example, if we say that if I remove cigarette smoking, alcoholism, completely the lung cancer or whatever cancer will be taken out from the community. Is that true? No, it is not. So basically the constant term tells you what is the baseline risk that everybody has, every community has. That is the use of constant term. Here today, that what we are saying, what do we say that, for example, in the drug B, drug A, the regression coefficient is B, 15. If 1 unit increase in your drug dose, 15 units change in your blood pressure. So if I increase the dose by 4 units, what kind of change happens in the regression? So that is a simple calculation which you do. Now, this is, I mean, just explaining this regression equation. These are all the assumptions which we have, that is independence. Observations are independent. But in repeated measures analysis, the observations are not independent. So we are violating the assumptions there. And homogeneity in variance. So what do we mean by homogeneity in variance? The y variable follows normal. Don't go for testing for normality and all that when you do regression analysis. It is nearly normal. Okay. We don't go for, we don't usually do any test to see, make sure that y follows normal. And similarly for the homoscedasticity or the homogeneity, yes. So the independence has to be satisfied. Okay, for example, I remember there was a outside obstetrician wanted to go for a Singapore conference. So nobody is there except CMC, she knows. She came to our department. She said she has got 500 observations of gestational age and birth weight of the babies, or sorry, biparietal diameter or something like that. So I said, how many women were studied? She said about 100 women or 90 women studied. So each woman has visited her 3 or 4 times. Okay, you understand? So now if you say I am a woman, I visited her 3 times. So I have 3 readings contributed, 3 gestational age and corresponding biparietal diameter. So therefore, shall I take this? She claimed that she has got 500 observations, but it is 90 women. Do you understand? Now you tell me whether am I dealing or is she dealing with independent observations or correlated observations? Correlated observations. Definitely today that you will not do that kind of simple regression analysis for the data. Okay, so that's something. And the normality is very important. It should not be very skewed or whatever. And the homogeneity and variance is, let me give you some examples. So there are indirect way of testing whether the data have equal variance across X variable that I'll tell you later on. So this is for a given variable, given X variable particular unit. If you look at the dependent variable, the distribution is normal. If you take 4 dose, all the responses are normal and have some kind of variance. All these variances are expected to be same. That is called homogeneity in variance. Oh, how do I do it? How do I test it? So you can do a test indirectly by looking at the residuals and so on. That is not necessary now. So we'll have a soft stand on this one. This is what I said. This is here. A woman come to. So this I explained to you, this estimated birth weight and so on and so forth, not independent observations. This is very important statistics called Wald test, t-test. So basically, Wald is a scientist who has found out this test. Standard error of the regression coefficient divided by, regression coefficient divided by standard error follows t distribution. Okay. So therefore, you need to see whenever you see any regression coefficient with standard error, and you look at the t statistics, and if it is greater than 1.96, that variable is statistically significant. Okay. This is Wald test. We call it as Wald test. So this is something which is not necessary. If we say it is not significant, does not mean that it is not significant. Probably the curvilinear relationship is modeled as a linear regression. Therefore, you did not find that as significant. Let us spend some time to understand this. Okay, this is analysis of variance statistics, the F statistics table. This is very important when you do regression analysis. Regression is one line which explains the variability, and that is this one. So therefore, the variability in the y variable, dependent variable, minus the error, sum of square due to error. Error is basically unexplained for a given model. And this is the residual variance. And this is whether that is significant as compared to this. The residual is basically chance variability, which can be reduced, but it cannot be completely eliminated. Please remember, that has to be there. If it is, unless you are R square, the performance of the model is very high, say 100% accurate, that it has to be zero. In ideal situation, it cannot be zero. If this becomes zero, your performance of the model is going to be very high. This is R square statistics. What is the variability due to regression divided by that, the variability of the dependent variable. So this is due to regression, and this is the variability of the y variable. The regression is able to explain 100% of your y variable, then the R square becomes 100%. Okay. This can happen, R square cannot be 100%. But animal studies like pharmacology, biochemistry, they do 6 animals, 5 animals. They're all grown in the same environment and so on. There you can get 60%, 70% R square. In the human being studies, you cannot get R square to 60%, 70% and all, unless the data has outliers. It's very difficult to get R square 20%, 30% in human being studies. So therefore, this is the R square is a very important statistics. It's called goodness of its statistics. In any conference or anywhere, if somebody presented R square is 80%, 90%, we don't trust the data. Okay. You should ask the question. If I do any analysis, if my R square is very poor, then I will not present it. Why should I present it? Why should I say it? But you should ask the question, what is your R square, to say whether I trust this model or not. So this is the multicollinearity is a very important concept. Say for example, that is one of the reasons when you do we are talking about regression multivariable analysis today. So this can happen in your regression analysis. So this is the cycle, and this is from my PhD thesis. Okay, don't ask me my R square, you get upset to that. So this is, say for example, the area is rural or urban. This is the gravida number of pregnancies. So this is a cycle length. This rural women had almost 32 days, whereas urban women had 31 days cycle length. First of all, it is not 28 days. Okay. So therefore, you see similarly, when you look at this data, the parity, 32 days and 31 days. So there is a good correlation between parity and gravida. Do you agree with me? Do you see a good correlation between the two? They are all mimicking the same, whether you use rural gravida or parity. Okay, highly correlated data. I did the regression analysis. Now, someone has to interpret the gravida regression coefficient and parity regression coefficient. One unit change in your gravida, one more pregnancy in your life. How much change in the cycle length? 0.26 days change. So I would expect similar results in the parity as well. Do you agree with me? Because they're all similar, except the abortion. So the parity is saying negative correlation and the value is 0.3. What does it say? It says that as parity number of live births increases, the cycle length decreases and so on. So do you agree with this? My boss started laughing about this analysis. He wanted to know this is because that parity and gravida are highly correlated. Cholesterol and fat is highly correlated. If you run a regression with highly correlated two independent variables, you'll end up with this kind of results, which is confusing. What another thing, what you do not know is this kind of correlation, how much have they affected the other regression coefficients? You understand? So therefore, the multicollinearity is a big issue here. Usually this is assessed by many statistics, the case statistics and variance inflation factor and so on. See, for example, when all other variables were around 1 or 2, the gravity and parity had values 11 and 14. It tells you there is a strong correlation going on between these two variables and will affect your regression coefficients. Okay. So what is the solution? So now you have many methods to handle this. Now, this is the simplest one is after 2, which is more reliable. My boss said women may not remember the number of gravidas, number of pregnancies, because the prolonged menstruation or this thing was considered as a pregnancy. Therefore, drop pregnancies and take live births. So we did this analysis, but you see now what is the correlation which is going on here? Okay. Absolutely, there is no correlation. You just correlate this result with the graph which I had shown you. No correlation. So this is because of, I have not told you about, you need to eyeball the data of other regression coefficients, see how much change has happened in your data. Okay. This is the regression adjusted method. You see, this is coming in a different direction, but the parity has a similar effect. If you do regression adjusted analysis for collinearity. Look at this data and tell me what is happening here. This is, we had an outstanding epidemiologist, obstetrics gynecology department, Dr. Mathai Matthew. So this is about his studies dealing with the 900 women. This is about if the lady is a passive smoker, what kind of decline happens in her baby's birth weight. Do you understand? So if you have a covariate called, the variable measured as she's a passive smoker, yes or no? Okay. So you need to see where is that variable, passive smoking, yes or no? What does this value? What does it tell you? Yeah, if I'm not passive smoker, 0. 1 means passive smoker. If you move from 0 to 1, there is a birth weight decline. Do you understand this? Decline in the birth weight, 62 grams reduces. So, which is significant also. I wanted you to look at gestation and gestation square. Are they not same? Say for now, are they not same or highly correlated? Say for example, if your gestational age is 25 weeks, 25 weeks square is 625. So if you do the correlations, both will go together. The correlation will be highly significant, 1 almost. So why should we have gestation and gestation square in the analysis? It introduces multicollinearity. Why should we have GA and GA square? Yes, this is what I said. The gestational age and birth weight have not a linear relationship. It has got a quadratic relationship. Now what I'm trying to say is, so you have to appropriately model it. Many times we don't do that. This is GA. This is what you get. the real life situation. If you do a linear regression analysis, you would land up with a curve like this. This is what the regression analysis says. If you put only one variable, GA versus birth weight. So when you put GA square, the GA square has a negative regression coefficient. What it does is, one allows you to go higher. Say, for example, like this, it will go here like this. The minus part will taper it down. So you get a curve like that. Do you understand? One is a positive correlation, it goes on like this. The other one is a negative correlation, means it will pull you down. So finally you get a quadratic shape. Therefore, when you have a curvilinear regression, you have to do the modeling like this. Is that right? Okay. Yes. Both should be there. GA square alone will have, I don't know, we'll have to try that out. What happens? Still, it is a linear. It is not curvilinear. It is going to be a linear. Okay. This is about the regression.